Okay, so we're going to talk about Descartes' rule of signs. And what that does is it tells us the number of positive real x-intercepts and the number of negative x-intercepts. And the way we're going to do that is by counting the sign changes in the function. After we count how many sign changes we have for f of positive x, we're going to go backwards by 2 because we can only count back by an even integer. And to find the number of negative zeros, we have to find f of negative x, and then we're going to look for our sign changes and again count back by an even integer. So let's go ahead and look at this first function. So for this first function, f of positive x, let's count how many times we have a sign change. So we started off with a positive, and we go from positive 3 to a negative 4. So we went positive to negative, so that counts as one sign change. And then we go from a negative to a positive, so that's another sign change. Positive to positive, that's not a sign change. Positive to a negative again, that is a sign change. And then at the end, it's a negative to a negative. So we have 3, f of x has 3 sign changes. So that means that we can have possible, this doesn't mean how many we do have, but it is possible that we have 3 positive roots or 1 positive root, because you cannot go backwards by 2. We have to go backwards by an even integer. So f of x has 3 or 1 positive x-intercepts. So now let's do the same thing for f of negative x. So when we go through and we find f of negative x, every place that we have an x, we're going to put a negative x now. And just remember your exponent. If you take a negative to a odd exponent, it will remain negative. But if you take a negative to an even, it is going to become positive. So we're going to go ahead, and I'm just writing that function, putting in a negative x every place that we see an x, so that we can go back and find our sign changes. So we're going to start here. We have a negative to an odd, so that is going to cause that to change sign. So that positive 3 is going to flip to a negative 3. So we have negative 3x to the 7th. Okay, so this is even. So because that's even, that negative will become positive, and that's not going to affect the sign of its coefficient. So odd exponents will change the coefficient. Even exponents, the coefficient stays the same. And also keep in mind here, this is to the power of 1, so that is going to change that to a positive x and then a minus 3. So now let's go back through and count our sign changes. So negative to a negative, that's not a sign change, not a sign change. So we get our first sign change from here to here. We don't have a sign change from 2x squared to positive x, but we do have one at the end. So f of negative x, we had 2 sign changes. So what that means is we can have two or 0 negative x-intercepts. Okay, so let's do that again with example B. So first we'll count our positive sign changes. So that's a no. This one here would be a yes. Sign change there. And that is our only one. We only have one sign change. So that means that f of positive x can only have one positive x-intercept. And of course we can't go backwards, because if we subtract 2, then we will have -1, which is not possible for the number of positive x-intercept. So it has one positive x-intercept. So now let's go ahead and evaluate f of -x. And I'm just going to keep in mind, again, if it's an even exponent, the sign stays the same. So this is even, so that's going to say x to the 4th. This is odd, so that's going to make that +7 flip to a -7. This is even, that's going to stay the same. This is odd, that's going to flip. And now let's look at our sign changes. So we have one sign change here, and then negative to a negative, that doesn't change. Negative to a positive, we have a change. Positive to a negative, we have a change. So that means that f of -x, we had 3 sign changes. So we can have 3 or 1 negative x-intercept. And that is the Descartes rule of sign changes. So the second part of 4.2 is finding the zeros. So we started off with figuring out how many positive and negative we could have. So how do we go about finding what those zeros are? So the first thing we need to do is identify what are the possible roots. So in order to identify the possible roots, that's the rational zero theorem, we're going to take p and divide it by q. P is the constant, q is your leading coefficient. So I'm going to list all of the factors of p and then all of the factors of q, and then I'm going to divide them. So let's start off by listing all of the factors of 6. Keep in mind that each number can be positive or negative. So all of my factors of p are 1, 2, 3, and 6. Those are my factors of p. And then my factors of q are just 1 and 2. So that means that I'm going to take these 4 numbers and I'm going to divide them by 1. And then I'm going to take these same 4 numbers and divide them by 2. And those are the possible rational zeros. So we're still dealing in the land of possibility, and then soon we'll actually go into finding what they actually are. So we have plus and minus. So I have 1 divided by 1, 2 divided by 1, 3 divided by 1, and 6 divided by 1. And again, keep in mind that every single one of these, again, is positive or negative. And now let's go back and take these 4 numbers and divide them by 2. So I have 1 divided by 2, so plus and minus 1/2. 2 divided by 2 is just 1, so we don't need to list that because we already have 1 listed. And then we have 3 divided by 2. And 6 divided by 2. Well, 6 divided by 2 is 3, and we already have that. So the possible rational zeros, or x-intercepts, we have plus and minus 1, positive and negative 2, positive and negative 3, positive and negative 6, positive and negative 1/2, and positive and negative 3/2. So let's do the same thing with example B. First, we're going to list p's. So we're going to start with our constant. In this example, the constant is 12. So what are the factors of 12? So we have 1, 2, 3, 4, 6, and 12. And then what are the factors of Q? So numbers that will divide into 10 are 1, 2, 5, and 10. So let's list our possibilities, and this is going to be a pretty long list. So we're going to start off again. All of these numbers, all 6 numbers divided by 1. So plus and minus. And we have 1, 2, 3, 4, 6, 12. Now we're going to take these 5 numbers and divide them by 2. Okay, so we have 2 divided by 1, which we already have. 2 divided by 2, we already have. 2 divided by 5. Wait, sorry. 3 divided by 2. So we have, let's start over. So we have 2 divided by 1, 2 divided by 2, 2 divided by 5, and then we have 2 divided by 10. Well, 2 divided by 10 can be reduced to 1/5. So I'm going to write it, but we're going to reduce that down to 1/5. So now let's take our third zero. So we have 3 divided by 1, which we already have. 3 divided by 2. And then we have 3 divided by 5. And we have 3 divided by 10. Okay, so now let's go to the fourth. So we have 4 over 1, which we already have. 4 over 2, which is 2. We already have that. And then we have 4/5 and 4 over 10. So 4/5 is a new one. But 4 over 10 reduces to 2 over 5, which we already have. All right, so now let's go to 6. So we have 6 divided by 1, which we have. 6 divided by 2, we have. 6 divided by 5, and 6 divided by 10. Well, 6 divided by 5 is a new one. And 6 divided by 10 reduces to 3/5, and we already have that one. So our last one, 12 divided by 1, we have. 12 divided by 2, 6, we have. 12 divided by 5. So I'm going to list that one. Let me go back to the front. 12 divided by 5. And then we have 12 divided by 10. Well, 12 divided by 10 reduces to 6/5, and we already have that. So that is how we find the possible rational zeros. And in our final example, we are going to begin actually finding the zeros.